Yeah, hello everyone. Yeah, today I am going to discuss about eigenvalue and eigenvector of a matrix. So let me start. Eigenvalues and eigenvector of a matrix. So what is eigenvalue and eigenvector of a matrix? If you are having if T be a linear transformation, let us assume that T be a linear transformation and X is a non-zero vectors. Let X be a vector. This is not equal to 0 and lambda be a real number such that T of x equal to lambda x. So in this case, if you are having, if T be a linear transformation and x be a non-zero vector such that T of x equal to lambda x, then this lambda is known as eigenvalue and this x is known as eigenvector. For example, let me clarify this. Suppose if you are having, let us assume that this is what x-axis and this is what y-axis. And let us assume that x be a vector which is given by 1, 2. This is, let us assume that this is x be a vector which is given by 1, 2. So what is meaning of eigenvalue and what is meaning of eigenvector? If we are having this vector 1, 2, if I am going to apply t here, if I am going to apply this t on this vector 1, 2, so this t of 1, 2, this t of 1, 2, this should be always multiple of some lambda times 1, 2. Then only we can say that this lambda is eigenvalue and this 1, 2 is the eigenvector of the matrix. So first, let me clarify why this x cannot be equal to 0. Because let us assume that if x equal to 0, then what will happen? If x equal to 0, if x equal to 0, then what you will get? By definition, t of x equal to lambda x. In this case, t into 0 equal to this, you will get t into 0 and this equal to 0 into x. So we are not going to get anything. So because of that, this x cannot be equal to 0. So this definition is for linear transformation. Same definition we can generalize for a matrix. If same definition we can generalize in case of matrix. Let A be a n cross n matrix and x is a non-zero vector. Let us assume that x is not equal to 0. Then this x is known as eigenvector and lambda is known as eigenvalue if A of x equal to lambda x. So what it means, as I explained you, as I explained, linear eigenvalue and eigenvectors means what? If you are having some vector, we can assume, again, I will explain. If you are having x be a vector, this 1, 2 or something. If you are going to apply t here or a here, so the resultant, if you are going to apply a in this vector, so resultant should be also in the same direction. Whether it is 2 times, whether it is 3 times, whether it is 4 times, but direction should be same. For if you are getting a of x equal to, if this quantity left hand quantity a comma x, if you are not getting in the direction of x, then this lambda cannot be the eigenvalue of the matrix. So according to the definition, if Ax equal to lambda x, if you are getting, then in this case, this lambda is known as eigenvalue and this x is known as eigenvector. So why this x cannot be equal to 0, as I explained? Because if x equal to 0, then we will not get anything because a into 0 equal to lambda into 0. So we are not going to get anything. So for existence of eigenvalue, this x has to be non-zero. If x equal to 0, then we are not going to get anything. So x has to be 0. Yeah, let me explain a simple example. Suppose if we are having given, if T be a linear transformation and T of 1 comma 2 is given, this equal to given 2 comma 4. So what we can say about eigenvalue and what we can say about eigenvector of this transformation. So same thing we can write T 1 comma 2 equal to, if I will take here 2 common, then this equal to what? 1 comma 2. So now we can compare with T of x equal to lambda x. So you are looking here, x is 1 comma 2 and here lambda equal to what? 2. So we can say if you are having linear transformation, T of 1 comma 2 equal to 2 comma 4, it means the eigenvalue of linear transformation is 2 and eigenvector is 1 comma 2. So this is meaning of eigenvalue and eigenvector. If you are having x non-zero vector and if you are going to apply linear transformation on a matrix, so resultant should be in the direction of this x. Uh, for example, if I am giving this example, suppose of t1 comma 2 is equal to 3 comma 4. So what will be eigenvalue and what will be eigenvector of this linear transformation? So is it possible to calculate? It is not possible. Why it is not possible? Because t1 comma 2 T1 comma 2, are we able to write this equal to some lambda times 1 comma 2? This right hand side, this 3 comma 4, is it possible we can explain in the multiple of 1 comma 2? It is not possible because we cannot get any lambda here so that that lambda multiplied into 1 comma 2 and we can get here 3 comma 4. So because of that, if you are having a linear transformation t1 comma 2 equal to 3 comma 4, then eigenvalue we cannot calculate here because this resultant is not given in the multiple of 1 comma 2. So this is meaning of eigenvalue and eigenvector. If we are having x a non-zero vector and we are going to apply some linear transformation on some matrix on this vector, and resultant should be in the same direction, whether it is multiple of 1, whether it is multiple of 2, whether it is multiple of 3, but it should be in the same direction. We can say also we have studied, we can stretch. If you are having this vector 1 comma 2 and if you are applying here t, so this should be also in the same direction. If this direction is changing, then that lambda or that cannot be eigenvalue and eigenvector. So now how to calculate? Let me explain how you will calculate if you have to calculate eigenvalue of eigenvector of a matrix. So let us assume that let A be a n cross n matrix and x is not equal to 0 and let A be a n cross n matrix. So according to definition of eigenvalue and eigenvector, this A of x, this must be equal to what? Lambda x. So Ax equal to lambda x, then what we can write? Ax equal to lambda x, where x is not equal to 0. X equal to 0 if you are taking, then you won't get anything. So for existence of eigenvalue, this x cannot be 0. So if I will solve again, then what we can get? A minus lambda into identity matrix, this into x equal to what? 0. So now if I will ask you, this is consider this is equation first. So what you can claim about this equation first? So equation first is a homogeneous system of linear equation. So for non-zero solution of this equation first, For non-zero solution of this equation first, this determinant of a minus lambda I, determinant of a minus lambda I, this must be equal to 0, and this is known as characteristic equation. This is known as characteristic equation, and this a minus lambda I, this determinant of a minus lambda I, if you are not equating 0, this is known as a characteristic polynomial. And if you are equating this equal to 0, then we will get characteristic equation. And root of this characteristic equation is known as eigenvalues. Now you can ask how this homogeneous system of linear equation having non-zero solution are then we have 2a minus lambda equal to 0. Let me clarify this you. Let us assume that if you are having two homogeneous equation, x minus y equal to 0, and second equation if you are having x plus y equal to 0. This you assume that equation first, and this assume that equation second. So if I will form the determinant of its coefficient, then what you can get matrix coefficient of x and y. So we can get 1, -1, 1, and here +1. So what will be determinant of this matrix? Easily you can calculate determinant of A is what? 2. So determinant of A is 0 or not 0? This is not equal to 0. Now let us solve these two equations. Then what you will get? Easily you can add these two equations. So we can get here 2 of x equal to 0, and this will imply x equal to what? 0. Now x equal to 0, then we can put in any of equation. We can get y equal to 0. So what you are getting here? If coefficient of coefficient of matrix obtained by this homogeneous system of linear equation, if you are calculating, then this determinant is what? Not equal to 0, but what we are getting? 0 solution. If x equal to 0 and y equal to 0, we are getting. So this is what getting 0 solution. So, but what I am saying, if you want to get non-zero solution of this system of linear equation, then you have to make determinant of a minus lambda I equal to 0. Otherwise, this homogeneous system of linear equation a minus lambda ix equal to 0, this is having only 0 solution. But we need non-zero solution. So because of that, we are taking a minus lambda I equal to 0. One more example. If suppose if this question is given x minus y equal to 0, and second equation if I will assume 2x minus 2y equal to 0. Equation first and equation second. Now if I am going to solve these two equations, if again I will form the determinant of the coefficient matrix. So 1, -1, 2, and -2. So in this case, what will be determinant of A? If you will calculate determinant of A, this is what? -2 and +2 equal to what? 0. So it means what? Determinant of A equal to 0. Then what you can conclude? So these two system of linear equation having non-zero solution. Non-zero solution means what? Because these two equations are what? These two equations are same, x minus y equal to 0 and 2x minus y equal to 0. So further, if you can solve, you will get x equal to y. So what are the solution of this homogeneous system of linear equation? 0, 0, 1, 1, 2, 2, 3, 3. So solution of this system of homogeneous equation, we are getting 0, 0, but here we are getting non-zero also. So if you are having system of homogeneous linear equation and you want to get non-zero solution of this system of linear equation, then determinant of coefficient matrix has to be 0. Otherwise, if you want to get 0 solution, then always you will get determinant of the coefficient matrix should not be equal to 0. So purpose of taking determinant of a minus lambda equal to 0, because we want to get non-zero solution. So let us assume that, so finally what we got, determinant of a minus lambda I, this equal to 0. By solving this equation, we can get if degree of this equation is dependent on the order of the matrix. For example, if you are having A is 3 cross 3 matrix, then this equation will be cubic equation. If you are having A is 2 cross 2 matrices, then you will get quadratic equation. So root of this A minus lambda equal to 0, this is root of these equations are known as eigenvalues, and x for which and x, this x for which ax equal to lambda x, this x if not equal to 0, then this x is known as eigenvector. So let us assume that one question, if we have to calculate eigenvalue and eigenvector of the matrix, so these are the basic concept. What is meaning of eigenvalue? What is meaning of eigenvector? Now I am going to calculate eigenvalue and eigenvector of the matrix. So let us assume that a matrix A equal to, one matrix is given 3, 2, and 2, and 1, 4, and 1, -2, -4, and -1. So this is a 3 cross 3 matrix, and we have to calculate eigenvalue and eigenvector of this matrix. So first of all, we have to calculate what? A minus lambda I, where lambda I is some real number and this lambda is known as eigenvalues. So what will be A minus lambda I? So this equal to this matrix 3, 2, and 2, 1, 4, 1, -2, -4, and -1, minus lambda into I. So what is I here? I is nothing but identity matrix of 3 cross 3. So we know that identity matrix of order 3 cross 3 is what? 1 0 0, 0 1 0, and 0 0 1. So now you can calculate what we can get. This equal to, so you are looking here when you will multiply this lambda into identity matrix. So in the diagonal position, we can get lambda, 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 remaining all the elements are 0. So easily we can subtract two matrices. If so, first entry you will get 3 minus lambda, and the second you will get 2, then 2, 1, and second element you will get 4 minus lambda, and 1, -2, -4, -1, and minus lambda. So this is what? A minus lambda I. Now for eigenvalue, we know that determinant of A minus lambda I, this has to be 0. Why this has to be 0? Because we need non-zero solution of this system of homogeneous linear equation. So when you will put determinant, so same matrix we can write down here in determinant for 3 minus lambda, and here 2 and 2, 1, 4 minus lambda, 2, -2, -4, -1, minus lambda, and this determinant should be what? 0. So again, now because we know that how to calculate determinant of 3 cross 3 matrices, but either you can do direct calculation, you can take 3 minus lambda and then you can delete first row and first column and then cross multiply this and this. But this process, because we have to multiply all the term, so better we can apply some row operation and column operation, and we can convert this matrix into some easy determinant we can calculate. So first, what we can apply? We can apply some row operation. R1 equal to R1 plus R2 plus R3. Reason why we are doing this one R1 plus R2 plus R3, why we are not doing here C1 plus C2 plus C3? Because if you will add here, if you will add first 3 minus lambda and 1 minus 2, so what we can go? 3 minus lambda, if I will add here 3 minus lambda, and R1 equal to R1 plus R2 plus R3, so plus 1 minus 2. So this is nothing but what? 3 plus 1, 4 minus 2. So you will get 2 minus lambda. Similarly, when you will add second, so you will get 2 minus lambda, 2 minus 2 plus 4 minus lambda, and plus minus 4. So plus 4 minus 4 cancel. Again, we can get 2 minus lambda. And similarly, in third also, we can get 2 minus lambda. Now we know that property of determinant, if we are having one element common in either in any of row or in any column, so we can take that element out. So what we can get? This 2 minus lambda, 2 minus lambda, and here also 2 minus lambda. Remaining all the elements are same 1, 4 minus lambda and 2, and this minus 2, minus 4, and minus 1 minus lambda, this equal to 0. So now you are looking here why we have done this row operation, because we want to take if you will add r1 equal to r1 plus r2 plus r3, so we are getting 2 minus lambda, 2 minus lambda. In the first row we are getting 2 minus lambda. So now this 2 minus lambda we can take outside, because property of determinant, if any elements are the common, so we can take outside. So 2 minus lambda we can take outside. So now what this determinant will convert into 1, 1, and here also 1, 1, 4 minus lambda, 2, minus 2, minus 4, minus 1 minus lambda, and this equal to what? 0. So now here you are getting 1, 1, 1. So again you can apply some column operation, so that because we know that if you have studied concept of determinant, so this determinant, if you have to calculate determinant of some matrices, so generally what we are doing, we are applying row operation and column operation, and we are trying to convert one row or one column, at least two elements are 0. For example, if I am able to make this 0 and this 0, and then we can expand our determinant about this first row. And either if second option, what is you are having, either you can apply column operation in the first column, and we will try to make two elements 0, and then we can expand our determinant along first column or first row. This is dependent on the column having maximum number of 0 or row is having maximum number of 0. So better we can apply, because we are looking here C1 also having 1, C2 also first element 1, and C3 also first element 1. So better we can apply C2 is replaced by C2 minus C1, and similarly C3 is replaced by C3 minus C1. So this matrix will convert into what? 2 minus lambda. And then what we are, because first column we have not touched, so first column we can write same. So you will get 1, 1, and minus 2. Second column 1 minus 1, we will get 0. And second you will get, because C2 minus C1 we are doing, so 4 minus lambda minus 1, so you will get 3 minus lambda. Similarly minus 4 minus 2, so plus 2, so you will get minus 2, because minus 4 and minus minus plus 2, so minus 4 plus 2 is minus 2. And third element you will get 0, 0, and here 1 minus lambda, and this equal to what? 0. So now our matrix, this determinant is converted into simpler way. So because now we have we are able to make this 2 0. So now we can expand our determinant along this row. So we can write here 2 minus lambda, and this we can take 1, and then we can delete this first row and first column. So 3 minus lambda into 1 minus lambda, and minus 2 into 0, 0. So this you will get what? 0. So finally 2 minus lambda into 3 minus lambda into 1 minus lambda equal to 0. So lambda value is 2, 1, and 3. 1, 2, 3. So this is the eigenvalue of the matrix. So basically what we have done, simply we have calculated determinant of A minus lambda I. And also in first time you have to understand concept properly. Second time, if you are having any matrices given to you, so simply you can subtract lambda from the diagonal element and put that determinant equal to 0. No need to put lambda into identity matrix 1 0 0 0 1 0 0 0 1, because it will take some time. So better you do directly you take matrix, and directly you can subtract lambda from the diagonal elements and put that determinant equal to 0. So sometimes we can get easy calculation. If you are not getting easy calculation, so we can apply some row operation and column options to make our determinant into some easy determinant. Because why I have applied this C2 minus C1 and C3 equal to C3 minus C1? Because I wanted to make 2 0 either in any of the row or in any of the column, so that we can expand our determinant along that row or column. So finally we are getting eigenvalue 1, 2, 3. Now next is how to calculate eigenvector. So again for eigenvector, we have to apply uh, concept of, so what is eigenvector and eigenvalue? Again we can solve by the given definition Ax equal to lambda x. So now because we are getting three eigenvalues, now each along corresponding each eigenvalue we have to calculate eigenvector. So first let us assume that we have to calculate eigenvector corresponding lambda equal to 1. Then what we will get? This will imply a minus, because lambda equal to 1, so you will get a minus identity into this x equal to what? 0. Many students, they can ask how we are getting identity here, because we know that a matrix and this lambda is a real number. So we cannot subtract a real number from a matrix. We can always subtract a matrix from a matrix. So because here lambda, we can multiply here identity, because identity multiplied by any number, we will get identity. So because of that, this lambda we can write here identity matrix. So this a minus I into x equal to 0. Now, what was given matrix A? Matrix A was given 3, 2, and 2, and 1, 4, and 1, and third is given minus 2, minus 4, and minus 1, minus identity matrix. Identity matrix always you have to consider same order. So 1, 0, 0, 0, 1, 0, and 0, 0, 1 into x. Because you are looking here, this is 3 cross 3 matrix. So this x, we can assume that x, y, z, this equal to what? 0. And always remember, this is 0 means this is 0 matrix, not 0 is 0 is not real number. This is 0 matrix. So now what we can get? A minus I into x equal to 0. So directly you can subtract 1 from the diagonal element. So 3 minus 1, 2, 2, 2, and 1, 4 minus 1, 3, 1 minus 0, 1, minus 2, minus 4, and minus 1 and minus 1. So you will get minus 2. Minus 1 and minus 1. So you will get minus 2 into x, y, z is equal to 0 matrix. So now we have to solve. So what we can get? So first equation, what you will get? First equation 2x plus 2y plus 2z is equal to 0. Second equation x plus 3y plus z equal to 0. And third equation minus 2x minus 4y minus 2z equal to 0. So now we have to solve these three equations, and we have to solve these three equations for x, y, z. So from the first equation, we can observe that we can get x plus y plus z equal to 0. And from the third equation, you can divide by minus 2. So you will get x plus 2y and plus z equal to 0. So once again, we can check calculation. A matrix is given 3, 2, 2. And 1, 4, 1, minus 2, minus 4, minus 1, minus I. Why? How we are getting I identity matrix? Because we are calculating eigenvector corresponding lambda equal to 1 eigenvalue. So 1 eigenvalue means this lambda equal to 1. So we can get a minus I, and I is nothing but 1 0 0 0 1 0 0 0 1. So you are looking here because non-zero elements we are getting in the diagonal position. So from 3 minus 1 we can get 2, 2 minus 0 2, 2 minus 0 2, 1 minus 0 1, 4 minus 1 3, 1 minus 0 1, minus 2 minus 4, and minus 1, and you subtract minus 1, so we will get 2. So this is correct. So first equation, because you are looking here, 2 is common. So x plus y plus z equal to 0. And second equation, minus x, we can multiply by minus x minus 2. So x plus 2y plus z equal to 0. So now if I will subtract these two equations, so x minus minus and minus, so x will be also cancel out and z will be also cancel out. So 2 minus y, this you will get y. So y equal to, we are getting 0. So now y equal to 0 means what? Y equal to 0 means what? Then we will get x plus z equal to 0. So x plus z equal to 0 means what? Z equal to minus x. So what is then how we can write eigenvalue? So because if you will look these three system of linear equation, 2x plus 3y plus z. So after solving these three equation, we are getting y equal to 0 and z equal to minus x. Y equal to 0 and z equal to minus x. In second equation also you can observe here, if you are y equal to 0, then z equal to minus x. So out of these two equations are same. So z equal to minus x. Now how to tackle this type of case? So better you can take, let x equal to k, then z will be what? Minus k, and y has become 0. So eigenvector, how to write? This eigenvector we can write first eigenvector x, y, and z, because capital X we have assumed that x, y, z, and x is what here? K. Y is 0 and z is what? Minus k. So k we can take common and we can get here 1 0 minus 1. So 1 0 minus 1 is the eigenvector of this matrix corresponding lambda equal to 1 eigenvalue. Now you can also ask, what about this value of k? So we can assume infinitely many values of k and we can get different eigenvector. So because of that, eigenvector of a matrix can be infinite. So this is dependent on k. So let us assume that now second case, let lambda equal to 1 we have calculated. Now let us calculate eigenvector for lambda equal to 2. So for lambda equal to 2, then how you will write? Ax equal to, again and again we have to use the definition, ax equal to lambda x. So this will imply lambda value is 2. So ax minus 2x, this equal to 0. So x you can take common. So a minus 2 identity matrix into x equal to 0. Again you can calculate a minus 2i. So a matrix was what? A matrix was given to us 3 2 2 1 4 1 and minus 2 minus 4 minus 1 into minus 2i. 2i means what? This we are multiplying identity matrix by 2. So no need to do first 2 then multiply I. Directly you can write a diagonal position 2 0 0 0 2 0 and 0 0 2 into capital X, and this X again we can assume that x y z and this equal to 0 matrix. So this what we can get first. So you can subtract 3 minus 2. This we can get 1. 3 minus 2 1 2 and 2. 1 minus 0 1. 4 minus 2 2. 1 minus 0 1. Minus 2 0. So minus 2 minus 4 and 1 minus 2 minus 1. 3 minus 2 1. 2 minus 0 2. 2 minus 0 2 and into this x y z, and this equal to what? 0. So first equation, what you will get? X plus 2i plus 2z, this equal to 0. Equation first. Once again, you can check our calculation. A matrix was given 3, 2, 2, 1, 4, 1, minus 2, minus 4, minus 1. So here I did mistake, minus 1. And 2i, so 2, 0, 0, 0, 2, 0, 0, 0, 2. So minus 1 and minus 2. So this entry we can get here minus 3. Minus 2, minus 0, minus 2, minus 4, minus 0, minus 4, minus 1, minus 2, minus 3. So now first equation, x plus 2i plus 2z equal to 0. Second equation, x plus 2i plus z equal to 0. Third equation, this is equation second. Third equation, minus 2x minus 4y minus 3z equal to 0. This is equation third. So from equation and first and second, we can, if you can solve equation first and second. So first, from the first and second equation, we are getting z equal to 0. Because here if you will subtract equation first minus second, so x minus x 0, 2i minus 2i 0, 2z minus z. So equation first minus equation second, and this will imply z value is 0. If z value is 0, then x plus 2i. So what we can get? X plus 2i equal to 0. And x plus 2i equal to 0 means x equal to minus 2i. So again, we can assume let x or y, we can assume k. So x equal y equal to k. So this will imply x value is what? Minus 2k. So now again we can write eigenvector x, y, and z. So this equal to x value minus 2k, y value k, and z value 0. So k you can take common again. So minus 2, 1, and 0. So this is second eigenvector, minus 2, 1, and 0. Last is we have calculated eigenvector corresponding lambda equal to 2 and lambda equal to 1. Now corresponding lambda equal to 3. Third case, eigenvalue corresponding lambda equal to 3. So lambda equal to 3. Again, we are having the given matrix. So we can get what was A matrix. Let me again write. So A matrix was given to us 3, 2, 2, 1, 4, 1, and minus 2, minus 4, and minus 1. Minus, now corresponding lambda equal to 2, directly you can write minus 3 identity matrix. So 3, 0, 0, because we are going to calculate eigenvector corresponding lambda equal to 3. So 3 means 3i. So 0, 3, 0, 0, 0, 3. And so this will imply 3 minus 3. So now directly I will write 3 minus 3 is 0, 2, and 2. 1 minus 0, 1, 4 minus 3, 1, 1 minus 0, 1, sorry, 1, and minus 2, minus 4 minus 0, minus 4, minus 1 and minus 3. So again, we can get minus 4 into, again, this capital X, we can assume that X, Y, and Z, and this equal to 0. So what you will get first equation? X into 0. I hope you are knowing that how to multiply. So first row and this first X, Y, Z. So x into 0, 0, y into 2, 2i. So first equation we can get 2i plus 2z. This equal to what? 0. So what we can get? Y plus z equal to 0. Second equation, x plus y into plus z equal to what? 0. And third equation, I think we no need to use third equation because first equation and second equation. From the first equation, we can claim that this y plus z value is what? From the first 0. So this will imply from second equation x value is what? 0. If x equal to 0 and we are having y plus z equal to 0, so it means y equal to minus z. So y equal to minus z, then if we are assuming that z equal to k, let us assume that z equal to k, and then this will imply y equal to minus k. So what will be eigenvector corresponding 3? X, y and z. This equal to 0. K if you will take common, because you know from 0 we can take any numbers common. We can take k common, we can take 1 common, 100,000, we can take anything common. So k value, y value is minus k and z value is k. Sorry, k we have taken common. So this we can write, k we have taken already common. So 0, minus 1 and 1. So this is third eigenvector of the matrix. So now how you will verify whether our answer is correct or not correct? So there is property of eigenvalues and eigenvector. What is property? Let me again write the given matrix. What is the given matrix? A equal to 3, 2, 2. What was 3, 2, 2? And 1, 4, 1. And minus 2, minus 4, and minus 1. So how you will verify whether answer is correct or not correct? So we have one property which I will explain later. Sum of eigenvalues. What is that? Sum of eigenvalues. What is sum of eigenvalues? What we have calculated? We have calculated 3 eigenvalues, lambda 1 equal to 1, lambda 2, 2, and lambda 3 equal to 3. So what are the sum of these 3 eigenvalues? Easily you can calculate 3 plus 2, 5 plus 1, 6. So sum of eigenvalues, this must be equal to trace of the matrix. What is trace of a matrix? Sum of diagonal element. So if you will add, these are the diagonal elements, 4 plus 3, 7 minus 1, 6. So we are getting trace A and sum of C. Second property is also there, determinant of A. Determinant of A, this must be equal to product of all the eigenvalues. Product of all eigenvalues. So by using this property, we can verify whether our answer is correct or not correct. And also you can verify uh, corresponding lambda equal to 3, because we know that Ax equal to lambda x, then x is known as eigenvector and lambda is known as eigenvector. If x vector, if let us assume that one eigenvector corresponding lambda equal to 3, we have calculated one corresponding lambda equal to 3. What eigenvector we have calculated? 0, minus 1 and 1. So this also you can verify this is correct or not correct. How you will verify? A matrix, this 3, 2 and 2, 1, 4 and 1, and minus 2, minus 4 and minus 1 into x. What is this x? 0, minus 1 and n. So this must be equal to what? Lambda times x. Lambda times 0, minus 1 and 1. So simply you can calculate that this product you will get 3 times of 0, minus 1 and 1. So it means this eigenvector 0, minus 1 and 1, this is corresponding eigenvalue 3. Easily you can verify if you will multiply these two. So easily we can multiply. If you will multiply this, then what you will get? 3 into 0, 0, minus 2 plus 2, then 1, 4. So this product we can write 3 times of 0, minus 1 and 1. So what it means? It means corresponding this eigenvector 0, minus 1 and 1, eigenvalue is given by. So this is the way to calculate eigenvalue and eigenvector of a matrix. Once again, I will remind you, Ax equal to lambda x means what? If we are having x a non-zero vector and we are applying any transformation on X or any matrix on X. If we are applying a transformation TX, then this must be equal to what? Some multiple of X. If you are not able to get in the multiple of X, then eigenvalue cannot be calculated. So always, if X is a non-zero vector and we are going to apply a linear transformation on or a matrix on X, so this resultant should be in the lambda times means what? It means this should be in the multiple of this X, whether it is 1 time, 2 time, 3 time, whatever it is there. So this lambda, what are the multiple? This is known as eigenvalue and this X is known as eigenvector. So next problem, one more problem. Let me explain about eigenvalue and eigenvector. So we have given one more matrix A equal to, we are having one more matrix 1, 1 minus 2 and minus 1, 2, 1, 0, 1 and minus 1. So now I can directly write what will be determinant of A minus lambda I. This equal to what? What we can write? Determinant of 1 minus lambda 1 and minus 2 minus 1 2 minus lambda. So directly you can subtract lambda from the principal diagonal elements. So it can save your time because if you will write A then minus lambda into identity, so better you subtract lambda from the diagonal elements. 2 minus lambda and here 1, 0, 1 and third entry minus 1 minus lambda. This must be equal to what? 0. So again, we can apply some row operation or directly you can calculate. It's up to you if you want to apply some row operation or some column operation. So this C1 we can apply because 1 minus lambda and minus 1 and 0 are given. So we can apply some row operation and column operation. We can convert this minus 1 0 or we can apply this one. Otherwise, you can apply direct calculation you can do. So we can apply here C1 equal to C1 plus C3. C1 plus C3. I will tell how this is benefited. If you will apply C1 equal to C1 plus C3, then what you will get? This equal to. So we are going to add first column and third column. So 1 minus lambda and minus 2. So what you will get? Minus 2 plus 1. So you will get minus 1 minus lambda 1 minus 2. And if you will add first column to third column, then what you will get? Minus 1 and plus 1, 0. And 2 minus lambda. And here 1. This is 0. 0 minus 1 minus lambda. 0 plus minus 1. So you will get minus 1 minus lambda 1 minus 1 minus lambda and this equal to 0. So why we have done this C1 equal to C1 plus C3? Now you are looking here minus 1 minus lambda and 0 minus 1 minus lambda. So this is 0. So here we can write 0 into minus 1 minus lambda. So we can take minus 1 minus lambda, we can take common. So this will imply you can take minus 1 minus lambda outside. So what you will get in the determinant? 1. We can check one more time whether we have written correct. This C1, this first column, we are, I hope you are knowing this is C1, this is C2, and this is what? C3. So we are going to add C1 equal to C1 plus C3. So this minus 2 and plus 1, minus 1, minus lambda. This minus 1 and plus 1, we will get 0. This 0 plus minus 1 minus lambda, so we are getting minus 1 minus lambda. So minus 1 minus lambda, 1 minus 2 minus 1, 1 minus 1, it will be 0. So 1 minus lambda you can take common. So 1, 1 minus 2 and 0, 2 minus lambda, 1. And here also we are getting 1, 1 and minus 1 minus lambda. And this equal to 0. So now directly you can solve because 1 minus lambda you have taken outside. So now this entire expression you can get in quadratic equation. So it's easy to solve. Otherwise we can apply R1 equal to R1 minus R3 because this here you are getting 1 and here also we are getting 1. So by applying this row operation R1 equal to R1 minus R3. So this 1 minus 1 we can make 1 0. So minus 1 minus lambda and R1 equal to R1 minus R3, 1 minus 1, 0, 1 minus 1, 0, because R1 minus R2 minus 2. So what we will get minus 2 R1 and plus 1 plus lambda. So this is nothing but minus 2 plus 1. So you will get lambda minus 1. And this is same 0, 2 minus lambda. And here 1. This is 1, 1 and minus 1 minus lambda. And this equal to 0. So now because these two are we are getting 0, so we can expand along first row. So lambda minus 1 and this into this into this. So finally we can get 1 plus lambda in one bracket because this minus 1 minus lambda we can multiply by minus. So 1 plus lambda and this 1 minus lambda and this 2 minus lambda equal to 0. So finally eigenvalue is what? Eigenvalue equal to 1, 2 and minus 1. So again we can calculate eigenvector corresponding each eigenvalues. So let us assume that first, I hope this is clear to everyone because simply we are doing some calculation a minus lambda equal to 0. And sometime directly also you can apply, but direct sometime you will get cubic polynomial like lambda cube plus 6 is 6 lambda square plus 5 lambda plus 2. So sometimes we can face difficulty to solving that cubic polynomial. But if you don't want to apply this row operation, column operation. So if you are getting like lambda cube plus 6 lambda square after multiplying all the elements of the determinant plus 5 lambda minus 5 equal to 0. Let us assume that this you are getting. So because cubic polynomial is not easy to solve, so better we can take lambda equal to random heat and trial method. We can apply lambda equal to 1. First we can check lambda equal to 1. If this is satisfying, so all the equation we can arrange in the form of lambda minus 1. So that lambda minus 1 we can take common. Otherwise, you can apply row operation and you can get your matrix in simpler form and then you can apply, you can expand determinant along any row or any column. So let us assume that eigenvalue first corresponding lambda equal to 2. Lambda equal to 2. So how to calculate eigenvector corresponding lambda equal to 2? Again, we have to start from the given matrix. So because we know that Ax equal to lambda x, so this and lambda equal to 2. So directly I can write here A minus 2 I into x equal to 0. What was given matrix A? So A matrix was given 1, 1 and minus 2, minus 1, 2 and 1, 0, 1 and minus 1. Minus 2i, directly we can write 2, 0, 0, 0, 2, 0 and 0, 0, 2 into x equal to again we can assume that x, y and z this equal to what? 0. So final matrix 1 minus 2 minus 1, 1 minus 2 minus 1 0 minus 1, 2 minus 2 0 and 1 minus 0 1 0 minus 0, 0, 1 minus 0, 1, minus 1 minus 2, minus 3 into x, y, z, and this equal to 0. So what we can get first equation? Minus x plus y minus 2z, this equal to 0, first equation. Second equation, minus x plus z equal to 0. Third equation, y minus 3z equal to 0. So these three equations we can solve. So from the second equation, we are getting x equal to z. X equal to z, either you can use in first equation or in second equation. So we can get y equal to 3z. So we were having three variables x, y, z, and we are not going to solve. We are getting relation x equal to z and y equal to 3z. So we can assume that let z equal to k. So z equal to k, then x will be what? K, and y will be 3k. So first eigenvector x, y, z, this equal to x value is k, y value is 3k, and z value is k. So k you can take common. So first eigenvector 1, 3, and 1. So this is first eigenvector 1, 3, 1 corresponding lambda equal to 2 eigenvalue. Similarly, we can calculate eigenvalue corresponding lambda equal to 1 and minus 1. So here lambda equal to 1 eigenvector we are getting. Just now I will write, you can verify. Lambda equal to 1, we can get 3 to 1. And for lambda equal to minus 1, we can get 1, 0, 1, 0, and 1. So this is the concept of eigenvalue and eigenvector of a matrix. Again, we can verify our answer by using the property. So given matrix, if you will calculate sum of eigenvalues 1 minus 1, 0. So we were getting three eigenvalues, lambda 1 equal to 2, lambda 2 equal to 1, and lambda 3 equal to minus 1. So according to the property of eigenvalue, trace of the given matrix A, trace of the given matrix A, this must be equal to sum of eigenvalue lambda 1 plus lambda 2 plus lambda 3. So trace of A, you can calculate 1 plus 2 minus 1, so 2, and this is also equal to 2. So trace of A and sum of eigenvalues are always equal. Next concept is Cayley Hamilton theorem. So what is Cayley Hamilton theorem? According to the definition of Cayley Hamilton theorem statement, every square matrix will satisfy its own characteristic equation. Statement here I will write, every square matrix, every square matrix satisfy its own characteristic equation. So what it means? For example, suppose if A is a matrix and A is 3 cross 3 matrix. Uh, Same example we can consider. Let us assume that A equal to some matrix as given like 1 minus 3 and 3, 3 minus 5 and 3, 6 minus 6, 4, this matrix is given. So you know how to calculate characteristic polynomial. So characteristic polynomial is nothing but what? A minus determinant of a minus lambda equal to 0. And this, let us assume that this we can get lambda plus 2 whole square into lambda minus 4 equal to 0. So according to Cayley Hamilton theorem, for example, if we are getting this, we can multiply and we can get some cubic polynomial. For example, let us assume that this we are getting after multiplication, lambda cube plus 3 lambda square plus 5 lambda plus 2 equal to 0. This is just I have assumed. This we can solve and we might be getting different. Just I have assumed that, let us assume that this we are getting lambda cube plus 3 lambda square plus 5 lambda plus 2 equal to 0. So what is Cayley Hamilton theorem? Cayley Hamilton theorem, according to the Cayley Hamilton theorem, every square matrix satisfies its own characteristic equation. What it means? It means if I will replace here lambda by matrix A, so what we can get if I will replace lambda by A matrix? So A cube plus 3A square plus 5A plus 2, because in matrix we cannot add real numbers, so we can take 2I and this equal to what? 0. So what is meaning of this Cayley Hamilton theorem? If you are able to prove that A cube, and how to calculate A cube? So we know that matrix A is given, we can calculate square matrix, again we can multiply same matrix, then we can get A square, and again one more time multiplication, we can get A cube. So if this expression A cube plus 3A square plus 5A plus 2 identity matrix, if you are able to prove that this equal to 0 matrix, this 0 means what? 0 matrix, this is not 0 real number. So if you are able to prove that this equal to 0 matrix, so you are done. So Cayley Hamilton theorem, according to Cayley Hamilton theorem, every square matrix will satisfy its own characteristic equation. So what it means? It means if you are having 2 cross 2 matrix or 3 cross 3 matrix, so first we can calculate characteristic polynomial and characteristic equation. And characteristic equation, if you are getting in terms of lambda, if that lambda, if I will replace by A matrix, and after doing all the calculation A cube plus 3A square and these things, if you are getting 0 matrix, so this is known as Cayley Hamilton theorem. Now, what is advantage of this method and why we are studying this Cayley Hamilton theorem? So Cayley Hamilton theorem is benefited for calculating inverse of a matrix. If you are asked to calculate inverse of a matrix, then you have studied an intermediate adjoint method, A inverse equal to adjoint of A by determinant of A. So in that case, you have to calculate adjoint of A, and then we can calculate A inverse. But by this method, easily we can calculate this inverse of a matrix. For example, if we are getting this characteristic polynomial, we are getting this A cube plus 3A square plus 5A plus 2I, this we are getting 0. So after this step, what to do, how we can calculate A inverse? So we can multiply by A inverse both sides. Let us assume that this is equation first. And how we are getting this one? If anyone is asking how we are getting this one, so we are getting this one by Cayley Hamilton theorem. Because according to Cayley Hamilton theorem, every square matrix will satisfy its own characteristic equation. So if we are getting characteristic equation of a matrix is like lambda cube plus 3 lambda square, this thing. So every square matrix will satisfy. It means what? This, if I will replace lambda by A, so we should get this equal to 0 matrix. So now in equation first, if I will multiply by A inverse, multiplying by A inverse in equation first, then what we can get? A inverse into A cube. So we can get A square. Otherwise, you can write down one more line, cube A cube into A inverse plus 3A square into A inverse plus 5 A into A inverse plus 2 identity into A inverse. This equal to what? 0. This actually by A inverse you can multiply either left multiplication or right multiplication. So this equal to, we can get A square plus 3A square into A inverse. So we can get 3A plus we know that a matrix multiplied by its inverse, then we can get identity. So 5 identity plus 2 I into A inverse. Any matrix multiplied by with its identity matrix, we can get same matrix. So I multiplied by 2A inverse. This also we can get A inverse, and this equal to 0. So what will be A inverse? So A inverse equal to this. Now we can put in left hand side. So you will get minus A square minus 3A minus 5 identity and whole divided by 1 by 2. So by using this concept, we can calculate inverse of a matrix. So now because A matrix we are having in our hand, so we can calculate A square. Again, we can multiply by A. 3A also we can calculate a matrix multiplied by 3. So we can multiply element 3 in each and every elements, and identity matrix you are knowing 1 0 0 0 1 0. So we can calculate this right hand side, this part, this matrix, and we can divide by 1 by 2, and we can get A inverse by using Cayley Hamilton theorem. So this is the advantage of this method. Actually, easily we can calculate inverse of a matrix. So let me discuss one example based on this. So let us A is given, a matrix A is given to us 2 minus 1 and 1 1 minus 2, sorry, minus 1 plus minus 1 plus 2, and here minus 1, and third element is third row is given 1 minus 1 and 2. So what is given question? Verify Cayley Hamilton theorem. Verify Cayley Hamilton theorem and find A inverse of the matrix, and find A inverse. So how to find A inverse by Cayley Hamilton theorem? So first of all, we can calculate characteristic polynomial and characteristic equation of the given matrix. So we know that how to calculate characteristic equation. Determinant of A minus lambda I, and this equal to 0. So now we have discussed some problem. Easily we can calculate. So when you will calculate this determinant of A minus lambda equal to 0, so this equation we can get lambda cube. I am going to write directly and you can verify. Lambda cube minus 6 lambda square plus 9 lambda and minus 4 equal to 0. So this is the characteristic equation of the given matrix A. Now according to Cayley Hamilton theorem, this characteristic equation must be satisfied by this matrix A. This is Cayley Hamilton theorem. So by Cayley Hamilton theorem, what we can write? This lambda is replaced by A. So A cube minus 6A square. So simply in Cayley Hamilton theorem, lambda is replaced by matrix A plus 9A minus 4 identity equal to 0. So this time, if you have to verify Cayley Hamilton theorem, this characteristic equation is easy to calculate. Why easy to calculate? This time you can multiply direct. No need to apply row space, column space. Why? Because this time we no need to do factorization of this characteristic equation. One thing you remember, if we have to calculate eigenvalue and eigenvector of a matrix, or we have to verify Cayley Hamilton theorem. So in both the process, you have to calculate characteristic equation. So for calculating eigenvalue and eigenvector, after getting characteristic equation, we need to factorize the given equation. But for Cayley Hamilton theorem, for verifying Cayley Hamilton theorem, no need to factorize. Simply we can get characteristic equation after multiplying, and then we can replace lambda by a. So now what will be a cube? What will be a square? Uh, I hope easily you can calculate. A square will be what? Same matrix multiplied by 2 times. 2 minus 1 and 1 and minus 1, 2 minus 1, 1 minus 1 and 2. Again, you can multiply by same matrix. 2 minus 1 and 1, minus 1, 2 minus 1, 1 minus 1 and 2. So what will be this a square? This a square easily we can calculate. We know, I hope you are knowing how to, this first row multiplied with first column. So 2 into 2, 4, minus 1 into minus 1 plus 1 and 1. So this we can get first entry 6, second minus 5, 5, minus 5, 6 and minus 5. Third row 5, minus 5 and 6. Similarly, we can calculate a cube. So a cube will be what? Again same matrix multiplied by same. Again same matrix. So 2 a square, because a cube you can write what? A square into a matrix. A square, just now we have calculated 6 minus 5 and 5, minus 5 and 6 minus 5, 5 minus 5 and 6 into same matrix A. A is given 2, minus 1 and 1, minus 1, 2 minus 1, 1 minus 1 and 2. So this we can easily calculate a cube, which is given by 22, 22 minus 21 and 21 minus 21, 22 minus 21, 21 minus 21 and 22. So this is our a cube. So now everything we have calculated. Now what to verify? We have to verify a cube. A cube, what we are getting? 22 minus 21, 21 and minus 21, 22 minus 21, 21 minus 21 and 22. Minus 6a square. So a square already we have calculated. This is what? This is a square, and this a square is multiplied by 6. So what we can get multiplied by 6? So 6 into 5, 30, minus 30. Sorry, 6 into 6, because 6 lambda is square, so this is 36, minus 30, and then 30, minus 30, 6 into 6, 36, and minus 30, 30, minus 30, and 6 into 6, 36. So this is a cube minus 6a square plus 9a. 9a, what you will get? 9a, a matrix was given 2. So 9 into 2, you will get 18, minus 9 in 9, minus 9 plus 9 into 2, 18, minus 9, 9 minus 9 into 18. So a cube minus 6a square plus 9a minus 4i. Minus 4i means 4 0, 0, 0, 0, 4, 0, 4, 0, and 0, 0, 4. So finally, you can calculate this calculation. You will get 0, 0, 0, 0, 0, 0, 0, 0, 0. So finally, if you are asked verify Cayley Hamilton theorem, so it's very easy to solve any question by using Cayley Hamilton theorem, and simply we can calculate A inverse. Now, how you will calculate A inverse? What was given characteristic equation after satisfying Cayley Hamilton theorem? We have got this relation A cube minus 6A square plus 9A minus 4I equal to 0. So finally, we are getting this relation. Again, this we can assume equation first. So we can multiply by A inverse in equation first. So this will imply A cube, A square minus 6A plus 5A into A inverse, 5 identity minus 4 identity into A inverse. So you will get 4 A inverse, and this equal to 0 matrix. So what will be A inverse? A inverse is this equal to 1 by 4, and this is A square minus 6A plus 5 identity. And everything you have calculated, we have calculated matrix A square also, 6A, we can multiply by 6 in matrix A, and 5 identity. 5 identity means 500, 050, and 005. So after doing these calculation, we can calculate easily A inverse. So A inverse, I will write direct answer. You can verify. Because A square just now I have calculated, you can watch, and A also we are given a 5I also we can calculate. So finally you can get 1 by 4, 3, 1, and minus 1, 1, 3, and 1, minus 1, minus 1, 3. So this is the A inverse by using Cayley Hamilton theorem. So I hope you understood the concept, because Cayley Hamilton theorem and characteristic equation. So till this step, we have to solve same for calculating eigenvalue and eigenvector. Also, we have to calculate characteristic equation, and for verifying Cayley Hamilton theorem, also we are getting characteristic equation. So Cayley Hamilton theorem by using we can calculate easily A inverse. Now, last topic, I will discuss what are the properties of eigenvalues and eigenvectors. So first property, as I explained, trace of a matrix, trace of a matrix A is always equal to sum of all eigenvalues. So this is very important property. So trace of A equal to sum of all eigenvalues. Second property is what? Determinant of a matrix is always equal to product of all eigenvalues. So how we can apply this these two property? So this is very simple. For example, let me discuss one problem. Suppose if A is a matrix of order, A is a matrix of order 3 cross 3, correct? A is a matrix of order 3 cross 3, and two eigenvalues of a matrix is given, 1 and 2. Suppose if A is a matrix of order 2 cross 2, and two eigenvalues are given, 1 comma 2, and then we have to find third eigenvalues or something like that. So by using property, we can calculate third eigenvalues. If two eigenvalues are given, 1 comma 2, and third eigenvalue is not given to us, so we know that, let us assume that third eigenvalue lambda 3 equal to what? Lambda. So we can apply property of eigenvalue. So sum of eigenvalue is equal to what? Trace of the matrix. So we can write sum of eigenvalues lambda 1 and lambda plus 1 plus 2. This is what sum of eigenvalues. And here this question we have to give trace also, because by if you are giving only two eigenvalues 1 and 2, so we are not able to calculate this third eigenvalue until and unless trace of the matrix and determinant of the matrix is not given. So let us assume that trace of A is given 3 and determinant of A is given 4. So how we can calculate third eigenvalue? Because two eigenvalues are given 1 comma 2, and third eigenvalue I have assumed that lambda. So by the first two property, sum of eigenvalues lambda plus 1 plus 2, this must be equal to what? Trace of this matrix. So this we can apply this equal to 3. So 2 plus 1 3. So lambda equal to what? 0. So third eigenvalue we can easily calculate by applying the property trace and determinant of the matrix. And sometime also we are getting this type of question: if a matrix satisfying this condition, A minus 2i, determinant of A minus 2i equal to 0, and one eigenvalues is given I. One eigenvalue is given I, then find determinant of the matrix. If A is a 3 cross 3 matrix and this is given condition, A minus 2i, determinant of A minus 2i equal to 0, one eigenvalues are given I, then find determinant of the matrix. So we know that determinant of A is what? Determinant of A equal to product of all the eigenvalues. Product of all eigenvalues. But here one eigenvalues are given I. So we don't know about two other eigenvalues, because here A is given 3 cross 3 matrix. If A is given 3 cross 3 matrix, then find determinant of A. Then how you will calculate? So this is also very simple to calculate, because we know that if determinant of A minus lambda equal to 0, so this lambda is known as what? Eigenvalue. So if you will compare these two equations, first and second, so lambda value is what? So one eigenvalue we are getting lambda equal to 2. And one eigenvalue is given I. Now we know that if any quadratic equation or any cubic equation, if one eigenvalues are I, then because this imaginary roots always occur in pair, so one eigenvalue is given I, then definitely this minus I is the second eigenvalue, because imaginary roots always occur in pair. So now we got all the three eigenvalues, 2, I and minus I. Now determinant is what? Product of eigenvalues. So 2 into I into minus I. So we know that I into I square, which is minus 1. So minus, because 1 already minus is there. So minus minus plus 1 into 2. So final answer we can get 2. So by using property of eigenvalue and eigenvector, we can solve some of question. This type of question will be asked in GATE exam or in any other competitive exam. They will be given to you one eigenvalue, and by using, they will give you trace, they will give you determinant. So by using this property, we can calculate remaining eigenvalues. So let me, next eigenvalue is what? If lambda is an eigenvalue of matrix A, then C lambda, if I am going to multiply by C lambda, then what will be, C lambda will be eigenvalue of this A into C. For example, if suppose A matrix having eigenvalue 1, 2, 3, if anyone is asking what will be eigenvalue of 2A, so simply you can multiply 2, 4 into 6. And if eigenvalue of A is given 1, 2, 3, then what will be eigenvalue of A square? So some students, they might be thinking first we have to calculate A matrix, then A square, then. So not like that, because if eigenvalue of A matrix is given 1, 2, 3, then eigenvalue of A square is what? You make square. So you will get 1, 4, and 9. If suppose you are having Eigenvalue of a matrix is given, A is given, eigenvalue of a matrix is given 1, 2, 3. Then what will be eigenvalue of this? A square plus 2A plus identity I. Then what you will get? First you take A equal to 1. Then what you will get? 1 square 1 plus 2. And identity is 1. So you will get 1 plus 2, 3 plus 1, 4. First eigenvalue. Second eigenvalue is given to A square 4 into 4. 4 plus 4, 8 plus 1. So you will get 9. Similarly, eigenvalue corresponding 3, you can get 3 squared 9 plus 6. 3 into 6, so 9 plus 6, 15 plus 1. So this we can calculate eigenvalue of A square plus 2A plus identity matrix. So these are the properties of eigenvalue and eigenvector. Fourth property is what? Matrix A and A transpose. Because we have studied A and A matrix always having A and A transpose always having same determinant. So A and A transpose also having same eigenvalues. And property 5, if lambda 1, lambda 2, dot dot lambda n are the eigenvalues of matrix A, then 1 by lambda 1, comma 1 by lambda 2, dot dot 1 by lambda n. These are the eigenvalue for A inverse. So just if you have to, if you are having matrix A and you are asked to calculate A inverse, so no need to find A inverse of the matrix. Directly we can write 1 by lambda 1, 1 by lambda 2, and 1 by lambda n are the eigenvalues of A inverse. Property number 6 is what? We know that a matrix is said to be invertible or non-singular. A matrix is said to be invertible if determinant of A is not equal to 0. So if anyone is asking you if any matrix A is having eigenvalue 0, 1, and 2, then what you can say invertibility of the matrix, whether this matrix A is singular or not singular. What you will answer, this matrix is singular matrix and this is not invertible. Why? Because we know that 0, 1, 0, 1, and 2 are the given eigenvalues, and we know that property of eigenvalues and eigenvector, determinant of A should be what? Product of eigenvalues. But if one eigenvalues are given 0, then 100% determinant of A you will get what? 0. Because product of eigenvalues, if you are having 10 eigenvalues and out of 10 1 is 0, then it will make 0 all. So determinant of A is 0. It means what? If any matrix having determinant 0, then it cannot be invertible and it cannot be non-singular. So by using these property, we can calculate determinant, trace. So this property we can apply. So now I hope this Cayley Hamilton theorem and eigenvalue and eigenvector is clear to all. And so in this lecture, if you are having any doubt, you can just comment, and if you are having any doubt, then I will clarify, or you are having any doubt or you are having any question which you are not able to solve. So you can write in comment and I will try to solve. And in next lecture, I will be discussing about system of linear equation, how to solve system of linear equation by using Gauss elimination and Gauss-Jordan method. So in this video, I have targeted you to explain about eigenvalue, eigenvector, Cayley Hamilton theorem, and some properties of eigenvalue and eigenvector. In next video, I will be discussing about system of linear equation by using Gauss elimination method and Gauss-Jordan method. Thanks.